All right, let's talk about an integrated rate law. So let's define what an integrated rate law is. So we've talked about rate laws. Rate laws tell us about rate constants and concentrations of the reactants. The integrated rate law also tells us the concentration at various times. So first we're just going to define what an integrated rate law is. It is a version of the rate law that also allows us to determine the concentration at various times. Okay, so I've written out the integrated rate laws for zero order reactions, first order reactions, and second order reactions. These are the only things that you are going to be asked. And here are the integrated rate laws. For a zero order, first order, second order, you would be given these. They will be on the formula sheet. You will have access to them in your textbook. They'll be given to you when you're doing your problems on SmartWork. You do not need to memorize these. You do need to know how to use each of these. So what A sub T right here. So this is the concentration of reactant A at time T. Negative K, K is our rate constant. T is time, usually in seconds. You'll see different units for time, but it's usually in seconds. And A sub 0, this is the initial concentration of reactant A. So we're only looking at one reactant in these examples. And you have to be told, must be told, or determine reaction order. Because you use a totally different equation depending on what order it is. So let's look at an example here. So here's an example, and it says cyclopropane is an anesthetic. The isomerization of cyclopropane to propene is a first order reaction. With a rate constant of 9.21 over seconds. If an initial sample of cyclopropane has a concentration of 6.00 molar, what will be the cyclopropane concentration after 1 second? .00 seconds. Okay, so here's an example of a word problem where you are going to determine which of these integrated rate laws to use, and we're going to solve this problem. So let's read through the problem. The isomerization of cyclopropane to propene. You don't need to know what that is. This is the reaction. You need to know that cyclopropane is the reactant because we only care about the reactants in chemical kinetics because we're not starting with any products. So the isomerization of cyclopropane to propene is a first order reaction. This is important because this tells me that I am going to use this equation because it's a first order reaction. You have to be told this, otherwise you don't know which equation to use. It's a first order reaction with a rate constant of 9.2 1/2 seconds. So that is K equals 9.2 1/2 seconds. Or you might see this written as 9.2 seconds to the -1. Those are the same thing. It says it has an initial concentration. If the initial concentration of cyclopropene has a concentration of 6.00 molar, initial concentration of cyclopropene is 6.0 molar. So remember the initial concentration, that is the initial concentration. A just represents any reactant. 6.00 molar. What will be the concentration of cyclopropene after 1.00 seconds? Time equals 1.00 seconds. And I'm solving for what is the concentration at this time. Okay, so we have everything we need. We're solving for concentration at this time. We're given the time, we're given the initial concentration, we're given K, and we're told what order reaction this is. So now we're just going to plug it in to solve for the concentration of cyclopropane after 1 second. All right, so I'm just going to plug everything in and see what I have. So natural log ln equals the concentration at some time, that's what I'm solving for, over the initial concentration, 6.00 molar, equals negative K 9.2 1/2 times T 1.00 seconds. So my units are going to totally cancel over here, 1/2 and seconds. So I'm going to be left with no unit. So that means my concentration at some time is going to be in molarity, which makes sense. So now let's see how we deal with all of this. So I'm just going to look at this side of the equation. I'm going to rewrite this whole thing. I'll say natural log of the reactant after some time over 6.00 molar equals, so now this side, negative 9.2 1/2 times 1 is going to be negative 9.2, nothing, no unit. So this is what I'm left with. So the way that we get rid of a natural log is we exponentiate it. We raise it to the e power. So if you look at your graphing calculator, make sure you can see this. And it doesn't have to be a graphing calculator, just any calculator that can do logs. So here is the log button. Log is a base 10 scale. This is not what we want. We want this, ln natural log. You see the second function above this natural log. It says e to the x. E to the x is how we get rid of the natural log. It will undo this. So I'm going to raise both sides e to the x. That's going to cancel my natural log. I'm going to raise this e to the x. So I'm going to say second natural log. So now it says e raised to negative 9.2. So now this is going to go on the other side. So now what I have is I've gotten rid of this. So I'm going to come down here and write all this again. I've gotten rid of the natural log, so it's going to be concentration of A at some time over 6.00 molar equals this number, 1.01 times 10 to the negative fourth. Again, no unit. So now to solve for the concentration of A at some time, the concentration of cyclopropane after 1 second, I'm going to multiply both sides by 6.00 molar. And what I get is the concentration of cyclopropane after 1 second times 6 is with, let's see, how many significant figures should my answer have? This is 2, this is 3, this is 3. So I should have 2. So my final answer should be 6.1 times 10 to the negative 4th. And what should my unit be? Molarity. Because remember, this is a concentration. So this is my answer. So let's think about all of this again. The question asks, when you have a chemical reaction of cyclopropane that is going to turn into propene, it's first order, the rate constant is 9.2, 1 over seconds. The initial concentration is 6.00 molar. In 1 second, the concentration of cyclopropane is 6.1 times 10 to the negative 4th. So think about that, how fast that chemical reaction is. That in 1 second, it's going from 6 molar to 6.1 times 10 to the negative 4th molar. So it's decreasing by 10,000 fold in 1 second. So this is how you do an integrated rate law. So obviously these will be different depending on what order reaction you have. If this was a 0 order reaction, you would have used this. If it was a second order reaction, you would have used this. You need to be told in the problem what order reaction it is, and then use the information to solve for the concentration at that time. Or you might see other examples where it says, this is the initial concentration, this is the final concentration. What would the rate constant be if this is the concentration change after this amount of time? And then you would just solve for the rate constant, or you could solve for the time. You could solve for anything in there. Most commonly, you're given this information like we see in this problem. You're given an amount of time, and then you're asked to solve for the concentration after that amount of time. So this is integrated rate laws. It's finding the concentration of a reactant after a certain amount of time has passed.